Very good. So what I decided or promised is that I would be reflecting on exascale computing, particularly on what exactly are we, what goals do we have, and where are we starting from? And so we've been asked a lot these days about what is our roadmap to exascale computing. And what I'm going to present here more or less will end up being our roadmap in Switzerland. And you will see, because we're a very small country, that we have to be a bit smart because we're working with a limited resource envelope. We cannot just, put in 500 million into a system or $1 billion into a system. So we take a slightly different approach. Now, I decided to start with this curve here that probably to Bill and some of you must be a provocation. But nevertheless, I will basically end up concluding that you were right with some of the criticism of the top 500 list. And so basically tracking the performance of supercomputers over time. But what I'm saying is we have to be honest. When we talk about exascale, nowadays we're not courageous enough anymore to say what we really mean is exaflop. Because all the systems you see, that are on the top systems on this list, they were designed to deliver a petaflop or 10 petaflops or 100 petaflops. It's just that today it's politically not correct to talk about exaflops anymore. That's why everybody talks about exascale. And then when we build a system that delivers some whatever flop on this benchmark, which in the past has been, the performance of which has been improving about 3 orders of magnitude every 10 years, then we go about and look for applications that deliver a certain performance. And so this is a material science application that I know very well. I was in Oak Ridge at the time. This was run the first teraflop. And then the first petaflop, that was a project I ran when I was still in Oak Ridge. And they pretty much track this list, the performance of the top systems. And then we go home and we say, we are happy with what we've done. You can actually go a step further, and what I'm showing here with these red dots is a particular type of application. So these are electronic structure codes that compute the Green's function. So Green's function-based electronic structure codes that use dense linear algebra. I think the one that probably many of you heard of is this LSMS code, or locally scalable or locally self-consistent multiple scattering theory, or linearly scalable multiple scattering theory code. And the precursor to that was a code called KKR-CPA. And this was one of the first codes that sustained the gigaflop. You pulled, and then we had LSMS in 98, and we had this Wang Landau LSMS code in 2009. And again, they show this 1,000-fold performance increase. So you can take one application and you can track this type of improvement. But the question I will ask during this talk is exactly what this means. And I guess you will see very, very soon it doesn't mean very much. Because I had a different data set available, and that is from ECMWF. This is the European Center for Mid-Range Weather Forecasting that has been founded in the late 1970s, and they've been tracking the performance of their application, which is a global weather model over the decades. So this is actually a time span that is quite a bit longer than the HPL even, because it starts in the 70s. And you see again, on the left side, you have the scale sustained teraflops. And you see again an exponential increase over time, but when you look at the numbers more precisely, then you see that this is increasing only at the rate of a factor 100 over 10 years. And when you look at, so you're measuring flops again, and we know that flops on HPL are increasing 3 orders of magnitude, at least between 1990 and 2010. Then you have to conclude, looking at this, that the weather and climate codes became 10 times less efficient every 10 years. Okay? And it turns out, well, that's the conclusion you have to draw if you look at flops. Okay? It turns out when you talk to these colleagues at ECMWF, they will admit that the floating point efficiency dropped from about 50% on the Cray YMP in the early 90s. So this is this purple system there in 1991, to about 5% on today's Cray XE system. So you have about a factor 10 over 20, 25 years, rather than a factor 10 every 10 years. So where is the rest of this difference in performance development coming from? There is one point that we tend to ignore when we look at this development of top 500, or actually those who have to pay the bill on the power don't ignore it, but everybody else ignores it. And that is the footprint of the system. So the systems have really changed in footprint. So what I'm doing here on the same plot, showing these multiple scattering theory codes that I discussed previously. And you see the factor 1000 and the factor 100. And you realize that in the early 90s, all these codes, whether KKR, CPR, or weather code, ran on a Cray YMP that used about 300 kilowatts, and the Cray XT5 or Jaguar in Oak Ridge in 2008, 2009 burned about 7 megawatts. And so there you see basically what's that, about a factor 20, 25 in increase in energy footprint. I don't know the size of the system, but must be of the same. Jaguar is a hell of a lot more. Today is Titan and is much, much bigger than YMP was still a machine, well, maybe a bit bigger than a table here and not filling a room like this. So, so clearly the footprint of the fastest systems in the world increased. It turns out, interestingly, the IBM Power 5, at least according to the top 500 entry, only used, at ECMWF, only used 400 kilowatts. So there you have another explanation to this discrepancy between weather and climate, because the weather systems are actually systems that have to be commercially viable. They are not, in some global race for supremacy in computing, but they actually produce something, and then you care about cost performance. Oh, maybe that was an inappropriate statement. Of course, the big systems also produce something, including the ones we build in Zurich or in Lugano. And interestingly, even at ECMWF, then the research I did showed that the power consumption actually has been going up, and they start to worry about power efficiency today. So still, so you can understand the differences, but you can relate the performance of different systems to each other. But from these plots, you can still not do much in terms of what, when are we going to reach what performance in the future. And performance based on, in the case of ECMWF, the model performance, which is the only thing that counts in the end. Now, we can take the same data, so the same models tracked over the years, but now looking at the complexity of the computation. So what we are plotting here on the y-axis is the complexity of the model measured in number of grid columns. So you have in a weather model, you have columns that are arranged on a mesh. And the number of grid points on a column can increase, and the number of columns can increase. And so that's 3 spatial dimensions. And then you have also the number of prognostic variables in the model that may increase. And so this is the number that is plotted here with the red curve for the different resolutions of the models. And then we can compare this now to different scaling factors. So what we show here with, forget about the Moore's law. One is assuming the performance doubles every 18 months, and that's about a factor 100 increase in performance every 10 years. Or you have assuming the performance doubles every 24 months or 2 years, and then I think you get 64 every 10 years improvement in performance. So remember before, when we look at flops, we would think the performance goes up a factor 100 every year. On the weather codes, you take the same data and you look at computational complexity, and then you see it's a different growth rate, doubling only every 2 years instead of every 18 months. Yeah? How do you know what's going to happen in 2035? Well, those are the projections of ECMWF, what their plans is. Now, and actually, thank you for the question, because this basically sets the stage now of the talk. This is assuming, I know the people at ECMWF quite well, so they are assuming somehow the system performance is going to increase somehow, okay? And we will have, well, you're laughing, but I will show you that it is possible. Actually, we will go even a bit more aggressive, and we will say, let's take the 1 kilometer. I will say the first part or next part after this introduction. I will argue or repeat arguments from my climate colleagues that will say there is something magic that's going to happen at 1 kilometer resolution that really makes it worth trying to pull in this milestone by about 10 years. And so there are good economic arguments, and so why you would like to have these high-resolution simulations in the early 20s and not in the 10 years later in the 30s. And so this talk will be about whether we can accomplish this. And because this is happening in the time frame when everybody else is building exaflop computers, that's why I'm calling it exascale problem that we are going to solve. So that's what the talk is mostly going to be about. And what I will now say is why exactly this is a magic number. And here I have to say I am a condensed matter physicist. I know about nonlinear systems and various things, but I'm not a climate scientist. So I rely heavily on my colleagues at ECMWF and ETH Zurich and Max Planck Institute of Meteorology for those statements. And then I will talk about where we are today in performance of these simulations. And then in the third part, I will try to analyze, what can we do? Is it realistic to promise these type of simulations early next decade? So one of the models we will be looking at is the ECMWF model, is IFS model, which is, in this country, we know the IFS model as the European model that gets the forecasts of the hurricane tracks right most of the times. And actually, statistically, when you look at the development of the accuracy, and this is this bar plot that is showing that actually ECMWF, this yellow bar, is doing substantially better by factors than all other models that we have available in terms of reliability of the forecast. But even though it may be the best model, it is still far away from being sufficient in accuracy and reliability. Now, what is known, of course, since a long time, and this is a work from a colleague, Pierluigi Vidali, and his collaborators, looking, and this was actually running on one of the Praise machines, the large tier 0 systems in Europe. When you look systematically at how the model becomes more reliable if you increase the resolution, you can already show it with this exact. So this is showing storm tracks in the Atlantic and how the agreement between the storm tracks predicted by the model and compared to observation is improving. It turns out when you push the resolution beyond 10 kilometers where they are today to a kilometer, there is something else that is believed to happen, and the colleagues say that the models start to resolve convective clouds. So today convective clouds are parametrized, and with a parametrization scheme that is not physically well justified. So when they parameterize radiation, you have Rayleigh scattering that is very well understood, the models, and you can actually build physically justified parametrization scheme. With convection, the way this is done today, it is far less possible. So it is one of the biggest sources of uncertainty or bias in these models. And it turns out, and this is work from a colleague at ETH, Christoph Scher, that you can look at convergence of when you don't parameterize convection, but you just let the convective clouds emerge out of the Euler equations and the equation of state that you're solving in these models. And there are two types of convergence you're looking at. One is what they call bulk convergence, which is just whether you get the area coverage of these clouds right. And the other is what they call structural convergence, is whether you actually get the size distribution and arrangement of the clouds right in a statistical sense. Now it turns out that when you look at the plot on the right, that is this bulk convergence, as you go from 8 to 4 to 2 to 1 kilometer horizontal resolution, when you look at the curves, 8 is quite off, 4 it starts to get better, and then between 2 and 1, somewhere you reach convergence, which means the area covered by convective clouds becomes correct or converges. In this case, there are other analyses that show it's actually correct, and then the energy balance in the model, because clouds reflect sunlight, and so the energy fluxes are properly resolved to within fractions of a percent, and that seems to be enough to run a climate model and to get statistically properly described model. On the other side, the structural convergence is far from reached, even at 500 meters. And so probably to get the convective clouds really represented properly in their structure, you would have to push the resolution down to 100 meters or maybe even further. But the real significant advance, and this is what Björn Stevens from Max Planck Institute of Meteorology is saying, the real significant advance is that we have sort of a properly, not a fully converged calculation yet, but we have a calculation that properly represents these convective systems. And so it's like an implicit but parametrization scheme that is correct. Implicit in the sense that it's implicit in the equations you're solving, and the area coverage is correct. There are also a number of other things that are believed to happen, like the orography is properly or sufficiently resolved, and we know this from our own simulations with MeteoSwiss, the meteorological service in Switzerland that is running their regional models at 1 kilometer, and they get the diurnal cycle for precipitation and wind, and so correct at that scale, and also ocean eddies and the pathology of the ocean. So there's really a strong indication that at this 1 kilometer things happen that are not incremental over the past, but are really going to change the value of these simulations. And of course, this is resolution. Now the other question is throughput or simulation throughput. And here what we are talking about is, how many years can I simulate, or how many days can I simulate in a certain amount of wall clock time. And the different applications of these simulations have, of course, different throughput requirements. In numerical weather predictions, you want to do like these 5 or 10-day forecasts in a few hours, not in 10 days, then they are not useful, but in a few hours they are useful, and that's how you go to this factor 100 ratio between simulated days and wall clock days, or simulated hours and wall clock hours. And then you can also use this metric that they say simulated years per wall clock day, and this is this SYPD that you will see a lot in the remaining slide. Climate simulations typically run over decades to a century, and you want to do that in a matter of maybe a few months. And that's how you get to this 1,000 ratio, or about 2 to 3 simulated years per day. And if you want to spin up a model, namely tune the parameters of the model, then you want to run it even faster. So the wish is, of course, to get much, much higher throughput, somewhere around 20 to 30. Now the question is, where are we today? So our goal will be, the minimal throughput that we have to have is somewhere around a simulated year per day. We would like to reach 5 simulated years per day, and I think you will hear similar numbers from Doug Cothy today for the tomorrow morning for the Exascale project in the US. We have worked very hard with our colleagues at ETH and ECMWF to come up with a very clear definition of what we mean by this kilometer scale, what vertical resolution, time step, and so on. I guess for this discussion here, we will just talk about 1 kilometer horizontal resolution, but what I mean is really the list of requirements that we have on this slide. Now the next question that I would like to address is, where are we today? Or more specifically, we are looking at the system that we have at CSCS, which is Stein, that was upgraded. The latest upgrade happened in late 2016. So we're really looking at where is 2016 technology with these 1 kilometer horizontal resolution simulations. And we are going to look at 2 models. One is IFS, and the other one is a model that we run for the meteorological service and our climate scientists, and this is Cosmo. And the reason I bring in Cosmo is because we have a lot of performance analysis, and so that we can discuss. With IFS, we're just starting this type of work in collaboration with ECMWF. Stein has somewhere around 5,300 nodes, hybrid nodes. It's actually a hybrid system that consists of hybrid CPU, GPU nodes and multi-core only nodes. We are only going to look at the hybrid partition, and we will have codes that in the case of Cosmo, that we can run either on the GPUs or on the CPUs. So we can really compare the two. IFS, we can only run on the CPUs. Now, why Cosmo? Because this is a code that we have been investing in. It is a model. Cosmo is a model that is developed by the German Weather Service, the Swiss Weather Service, a number of, I think about 6 or 7 weather services, and about 50 or 60 university groups around the world. It's very similar to WRF, probably runs a bit more efficient than WRF. And the reason I'm discussing it here is in the collaboration with Meteor Swiss, we ended up refactoring the whole, or rewriting the implementation of the model so it would run both on CPUs, GPUs, and today we actually have a version that would run on Xeon Phi if that line of product was continued. And so this was in 2015, the news that NVIDIA was mostly pushing out, that GPUs can be used for operational weather forecasting, which is a step beyond in terms of operational requirements than what you are used running on Blue Waters, or we are used running on Bitstein. Just briefly, the reason why Meteor Swiss was actually willing to work with us on this GPU port is the following. So they had a system that we bought for them in the last one in 2012, and were operating a 2-kilometer resolution model. And then they had plans to deploy a new model in 2016 that would run a trajectory at 1 kilometer and then run an ensemble of trajectories and better data assimilation. And if you add all these new requirements together, they would need a system that had a factor 40 more performance, but only 3 years after we had bought the first system. And they did not have a change in budget, so the budget was constant. And so where do you get the factor 40 in 3 years? Because the system has to be operational a year before they deploy the model, because they have to run through four seasons to make sure the new model is actually better than the old one. So where do you get a factor 40 at constant budget in 3 years? And it turns out, rewriting the model that had started already before because of Bitstein and the design of Bitstein, the ability to choose between GPUs and CPUs and so on helped. And I will quickly summarize. This is going away from the Exascale problem, but it's just showing how you can get these type of advances, that go well beyond what you get from Moore's law, and where you have to look for improvements if you go beyond, if Moore's law stops and you just have to rely on other things. So in this case, what we are looking at is the model, how it runs in Germany at the Deutscher Wetterdienst, or German Weather Service, and we can compare the same model with how it runs at CSCS, with the new implementation, but on both on Cray systems with multi-core. And you can see just from the rewrite of this model, we have almost a factor 2 in performance improvements. Now, this is starting from a professionally written code. When you start with not so well-written codes, and you see the NVIDIA advertisement for GPUs that have a factor 100 improvement, usually is factor 10 coming from rewriting the code and just running it on the same processors. Then, because we have rewritten the code, we can, of course, make a number of improvements like mixed precision or single precision, and improve resource utilization, and that turned out to be almost a factor 3. Change in architecture, so going from CPUs to GPUs, was roughly a factor 2. And then, so the first 3 arrows here, the green arrows, represent about a factor 10. And the rest was then Moore's law or architectural improvement over the 3 years that were going to happen anyway, and we did have to add more sockets. But in the end, the overall energy consumption of the system is actually lower because the GPUs were more energy efficient. So while their peak consumption is higher than CPUs, when you run a bandwidth-limited code, it turned out to be more efficient than CPUs. And so from the reduction in power costs, we can actually fund the person who is maintaining this new implementation. So, yeah? Yes. In this, okay, so this is the architectural improvement on the CPUs. We had over the same time frame similar architectural or performance improvements on the GPU side. So that's what I mean with this factor 2.8. This is something that the improvement that would have happened anyway, you know, by just waiting and not changing the code or anything. But then we have, in addition to this improvement, by moving to the GPUs, we have a factor 2. So this is comparing running on Haswell versus running on, this was, I don't remember so it's not K20X, it's the K80, I think they are using in that. And then this model for Meteor Swiss is running pretty much only on GPUs. So the machine is mostly GPUs, a few CPUs for post-processing. But that's when you have a unique application running. You can, you know, really design the system for that application. So this is really the background behind Cosmo. And since we have a lot of performance analysis that we will use, I'm also using this code. So we can now use this code, which is a limited area model running over the Alpine region or over Europe, using boundary conditions and initial conditions from the global IFS model. We can use this code to scale basically the grid to the globe. And this is not efficient. Okay, I will come back to this, but it still gives us a feeling for where would we be performance-wise if we were to run a global model with this GPU-based technology. And so that's what they did here. So you take this Cartesian grid, you wrap it around the globe with boundary conditions, and you run it from, I think, plus 80 degrees to minus 80 degrees. So it covers about 97% of the globe. It's inefficient because it becomes a lat long grid. So the grid spacing near the globes is very, very close. So it's non-uniform, and that has implications. You have more grid points than you need. You need more time steps to be stable. But you can still run it, and you can see what is your performance. You can do scaling at different resolutions, and just a reality check. In 2016, there was a Gordon Bell Prize winner for a simpler version of this same baroclinic instability test that was running on the Taihu light system in Wuxi in China, the #1 system on top 500. And when we compare the performance of Cosmo running on Bit-Steint to the performance of this Gordon Bell winner, we are about a factor 2.5 faster, doing an honest comparison. And so this is a system that from an HPL point of view is 5 times more performant than Bit-Steint, but you know, on the application it ends up being slower. Now we have done the analysis for Cosmo, and as I said, we've also done the runs with IFS on the same system. And then we can go through our requirements table, and we can say, for example, Cosmo, you know, it really ran at 1 kilometer. IFS ran at 1.25, so IFS has a shortfall of 1.25. Cosmo is about at 1. Both models ran at 60 levels. We need 100 180 levels, so we have a shortfall of 3. Cosmo ran at 0.04 simulated years per day. In the early 2020, we want 1 simulated years per day. That's why Cosmo there has a shortfall of 23, IFS a shortfall of 11. And then you add up all these numbers, or of course, logarithmically add up or multiply them. And then you see that Cosmo has a shortfall of 65x, and IFS a shortfall of nearly 200, 198. Okay, so the next part, so this is where we are today. So we could run 1 kilometer, it's just too slow and you know, not at the right scale. So what I would like to do now in the remainder of the time is really try to understand how efficient are these codes, and I will look at Cosmo because we have performance analysis for that. And then, you know, is it realistic to get to this to reasonable throughput in the early 2020s, and what do we have to do to get there? And the analysis for IFS we're in the process of doing, so I don't have much to report there. But for Cosmo, of course, we've been at this for a while, and this is really where Thorsten Höfler, and who is another collaborator that you know very well in the Blue Waters project, he's now at ETH Zurich and has contributed a lot here. So as I said earlier, just looking at flops in a weather and climate code turns out not to be useful. You will find you sustain a very low fraction of peak. And the reason is because these are codes that are algorithms that have a very low arithmetic intensity. And so you have to be very focused on the memory subsystems when you look at the performance. And it turns out also when you look worry about energy efficiency and everything, given today's architectures, today's physical constraints that we have on the processor, we need to really look at how efficiently are we using the memory. Now, you then are tempted to say, well, let's not look at flops, let's look at bandwidth and sustained bandwidth. It turns out when you think a bit deeper about this, that's also not enough. You need to look at 2 things. And this is this product of 2 numbers. One is called I/O efficiency, and the other one is bandwidth efficiency. And let me quickly explain. So the I/O efficiency is the ratio of necessary data transfers compared to actual transfers that your implementation of the code after compilation is actually doing on your architecture. So for both, you need a performance model that look at the DAG of the system and the constraints of your architecture. And it turns out you can estimate the necessary transfer and also measure the actual transfers. And for the Cosmo model, you get a ratio of 0.88 or almost 90%. 1 would be the maximum. If your actual transfer are just the necessary transfer, then you would have 1 there. So we are actually, with the implementation of Cosmo and of course the knowledge that the people who wrote the stencil libraries underneath had, very close to optimal. Turns out the other part, which is the maximum achievable bandwidth and the achieved bandwidth, this ratio, which we call bandwidth efficiency, is lower than actually 76% is the number if you compare the achieved bandwidth to streams bandwidth. If you went on the Pascal GPU to compare to peak bandwidth, you would be more around 50%. And now you can go in and analyze why is the achieved bandwidth so much lower. And what you will find is, you know, we have the streams bandwidth, and then you can look at different stencils, or it turns out the answer is that Pascal here, the Pascal GPU is not doing very well if you move away from stride 1 still structured memory access, but no longer stride 1. You drop almost to 50% of the peak bandwidth. Now, the important part of this analysis is because it shows you the memory use efficiency is composed of 2 parts. One is the part that the application programmers controls with the code, the way the code is written, and the other part has to do with how scatter-gather or the memory subsystem is working. And here, the answer that we get out is the homework is now on the people who designed the memory subsystem. And the application developers have actually done their homework. If you don't do the analysis this way, you just say, well, the application runs at 50% or even, of peak, which obviously is not, the responsibilities in this case not in the hands of the application developers, but of the system architects. So now, given that we have a metric of performance, we have identified where the problem is, given what we know about Cosmo, how realistic is it to overcome this factor 65? It turns out, as I already mentioned, the grid that this Cosmo model is running on is good for limited area model and is very inefficient for global models. And we know for global models what to do. From a mathematical point of view, you use either a cubed sphere or an icosahedral grid. Now the plan of record for MeteorSwiss is to switch to the icosahedral grid. So that's going to happen anyway, or is happening now, the development. And that means there will be 2 times fewer or only half the number of grid points. That's a factor 2. And then the experience MeteorSwiss has with running 1 kilometer scale on a regular grid, the time step would be 10 milliseconds instead of 5. So we end up just by changing the grid, which we will do anyway, we will get a factor 4. Now looking at this bandwidth argument that I just mentioned, if we improve the memory use efficiency and particularly by improving the bandwidth efficiency of the processors, we can get a factor 2. And it turns out the experience with Volta, which has an improved version of HBM2 compared to Pascal, this factor 2 is actually realistic. So we are already a factor 8 of 65 is already half of the factor 64 or 65 can be worked away by improving software and improving the memory systems in a way we know how to do. Then there is scalability. You can look at the scaling curves and you can say there's at least a factor 4 to 5 in weak scaling that we can get out, but we have to remember that we have half the number of grid points, so we've reduced the amount of parallelism, and so we can get a factor 2 at least. So again, from 65, 64, a factor 16 we can just get by normal developments. And so all that we are left with is a factor 4 that we somehow have to deal with, either through different processor architectures, improved memory architectures, near memory computing, or things that are going on, or improved algorithms, because the time stepping schemes in Cosmo is relatively simple, and there's things we can do from a physics point of view. Remember, the requirements is not 10 milliseconds, but is below 1 minute, so we could go to 30 milliseconds or 40 milliseconds, and if we have algorithms that are stable at that scale, then we could get an improvement. So I am quite confident that these type of improvements towards kilometer scale resolution, if we really take the problem holistically, are actually realistic to be solved within the next 5 or so years. The important point is that we cannot increase the footprint of the system, and there's a number of reasons. First of all, the budget envelope of CSCS I cannot just change like they did in DOE, but there is actually a deeper reason, and the deeper reason is, so far we've been talking just about one trajectory, and if we can run one trajectory in 2021 at this performance on a system like Bit-Stein, the climate scientists will have enough productivity to really try to improve and tune the models. But let me see, why is this not? Yeah, because it's PDF, the animations don't work. But what you really need is not one trajectory in production, you need an ensemble of trajectory, and this is, I believe, Hurricane Irma, or last year that went through Florida. And here you see the forecast 4 days in advance, which is pretty much saying evacuate Florida. And then when you look, the other picture is when at 1 day in advance, when it's somewhere in Cuba, and you really see, yes, it is coming through Florida. And then I think the result was really going through Florida, the hurricane. But what this means from a modeling point of view, running one trajectory is not enough. We need to reduce the footprint of the simulation significantly to run 20, 40, or 50 simulations in a given time frame. So in addition to the one simulated year per day that we would like to reach in 2021, we will have to improve the throughput to 5 simulated years per day for the climate people, and or reduce the footprint by roughly a factor 10. So I hope I've shown that even though we cannot just sit and wait for Moore's law to take care of all our performance model problems in the future, if we are creative and we are taking a look at the entire system, going from hardware to the drivers, that manage your memory system, to the application software, the libraries, everything, that actually we can still significantly improve of what simulations can accomplish. Now, Bill, how much time do I have? Okay, well, I have... I'm not going to take much more. But there's one other thought. So far I've been focused totally on performance of the simulations. Imagine we are successful, and in 2025, the climate models, the throughput, everything is such that everybody around the world is running at 1 kilometer scale. And of course, there are certain things they do not at 1 kilometer that they do coarse grain, but let's assume CMIP, the climate modeling comparison project, is running, the base is running at 1 kilometer in 2025. It turns out, I don't have the numbers here, so I have to remember them. I think CMIP 5 is where they were, so CMIP 6 is being discussed and run now. 5 ran or is done, and we know the data. Those were running at about 50 kilometer resolution, and the data was around 2 or 3 petabytes that were produced by these simulations. So if you go from 50 to a kilometer and you don't change the workflow, you will get to tens of exabytes of data. So if we really move forward and we are successful with the reference architecture from a performance point of view, and everybody around the globe can build these systems, including you at Blue Waters or Illinois on the successor of Blue Waters, then you would have to have tens of exabytes of data. And just to give you a scale, we have other projects discussing with CERN and the high luminosity upgrade. their Atlas CMS today, we're talking of the order of 800 petabytes of data. And they are talking about when they increase the luminosity by 23, when they ramp up the new upgraded LHC by 25, we're talking about of the order of 5 to 10 exabytes of data. If we are successful with this climate modeling and we don't change the workflow, we will deal with, CERN will not be the big problem on data. It will be a small problem compared to that caused by climate simulations. Obviously, this is not sustainable. And so we have to think about changing the workflow. And the proposal is actually something that some of people who do simulations in other fields is, you don't write out the data that you analyze, you write out checkpoints or the state of the simulation in a smart way, not just dump the memory, but in a smart way. You understand how you wrote the code and the model, and you understand what you have to save in order to have the state stored so that you can reproduce. And so the idea is you time these checkpoints in such a way that they represent intervals that you can run, say, in a day. And so you would run a trajectory on a very lean machine without any data or only minimal data analysis as fast as you can, store the checkpoints, and then rerun the simulation. And it's a bit tricky but solvable to rerun in a bit reproducible way or with controlled accuracy. But that's a problem when you get Thorsten to talk about it. He will say it's a solved problem. And then you analyze the rerun of the simulation in core. So you never generate these petabytes or exabytes of data. The checkpoints, we're talking about orders of magnitude less data that you're storing. So in conclusions, I hope I've showed that while looking at floating point operations per second, in terms of a historic comparison of past systems, that may be a good way to look at things. It is not useful or not a good metric to work with when you look at systems that you design for the future. Rather, we propose, or I think you need to look at memory use efficiency, and this is what we found, that this is a product of two things, namely how well your code is implemented and how well the memory subsystem works, how well the bandwidth can be used efficiently. We are certainly going to embark on this problem of kilometer scale weather and climate simulation in the design of future systems, because this represents really a big leap in the quality of weather and climate simulations. The aim is to really pull in this milestone that normally would be reached in the 30s, pull it into the early 20s. I think I've shown you there's a number of things based on what we have today, which is the fruit of significant investments in the last 5 to 7 years. But based on what we have today, with a set of reasonable, not outrageous improvement or achievable improvements, that we can actually achieve this goal. And this is what we call our roadmap to Exascale. But I am refusing to make any statements about what flops this system will have, because we will find out. And maybe it will not be much, maybe it will be more than we expect, who knows. Thank you. These are the collaborators I would like to acknowledge, mostly climate scientists and Thorsten Höfler. Thank you.
So let's thank Thomas for a great presentation and a lot of insight. I think we have time for a few questions, if anybody has questions about what Thomas has presented or talked about, or even if he hasn't talked about it yet. Anybody have any questions?
Hi, Lee Orff. I'm a weather modeler and from the University of Wisconsin. I do tornadoes. How many people do you have working on the code dedicated to this problem? To improving the code performance?
Okay, so actually the work on Cosmo was done with about a handful of people, maybe even a bit less. This was a quick and dirty first implementation of this new idea. That's a whole separate talk, the software architecture that we have in mind here. In the meantime, we have, I would say, about 10 to 15 people, because we're talking about the software is a stencil library with all the things you need to communicate between nodes and so on. So I call this a domain-specific library, or DSL. Some people call it language, and there is some loop language in it and so on. And the re-implementation of this in something that we call grid tools now is about 10 people working on that. But it's because we're trying to make it, this is more than Meteor Swiss needs, but we're trying to bring it into a shape where it can be used in other climate models as well. But it's not an outrageous number of people. And actually the investment that we made for Cosmo, the refactoring, was probably around 3 to 4 million Swiss francs. The system was of the order of 2 million that we deployed. If we did not make that software investment, the system would have to be 5 or 10 times bigger. So pretty much the software investment was amortized just with this one case of Meteor Swiss. And that's why it really pays off, okay?
Steve?
Are there tools to measure the I/O efficiency, or do you look at the assembly code or something else?
No, so that, it turns out, is not so trivial. And so proposing the new metric is easy. How to actually measure it is not. You need a performance model. So one thing is you need the DAG of your application. And with some of these newer implementations like grid tools-based version of Cosmo, it's easy to generate the DAG, but then you need to partition the DAG according to the performance model that you have and the constraints of the machine. And that is, at least at the moment, is non-trivial work. But again, it's the right thing to look at, so you have to do the work. If you get a meaningful number out, then it's worth doing.